Sounds like it. All right, so my name is Dari Kimanius, and I'm a postdoc at the LMB in Shore-Scaris lab at the LMB. And the last couple of years, I've been applying machine learning methods in single particle cryo-EM reconstruction. And today I'll be talking about methods for automation and improved robustness in single particle analysis. So I'm primarily interested in the right-hand side in this figure, where, well, the left-hand side is the where you do the motion correction and particle picking and particle extraction. And then you pull it into iterative refinement procedure where you have a model that you iteratively refine, or you have an ensemble of models. I'm primarily interested in that part, and that's what I'm going to be focused on. And the most of the ideas that I'm going to be talking about is going to be single particle, but some of them can also be extended to tomography, for instance. So when we talk about robustness in an algorithm, we're talking about its ability, the algorithm's ability to handle noise. When you, for instance, it relates to convergence, and if it's basically if the more noise, how much noise can you throw at the algorithm before it starts diverging or stop converging. It also relates to consistency, how much you change the subset or how much you change the initial model or initial parameters before you start getting different results. Now, robustness is extremely desirable in any algorithm. I can't really think of an algorithm where robustness would be a bad thing. There might be something out there, but it would be very, very exotic. But in particular in cryo-EM, robustness is a very challenging topic because of the amount of noise and all the number of parameters. We have an incredibly large number of unknowns that we try to refine and optimize. So when talking about robustness, regularization is a very related topic. Most of you have heard of the Bayes theorem. And yeah, basically, it tells you how you should combine previously known information with newly acquired information. Y here being the data, X is your model, and the prior is basically over your model, and you have the likelihood term and the prior term, or the log likelihood and the log prior term, and it's in cryo-EM is pretty straightforward to assign expression, an explicit expression for the likelihood term. However, the prior is typically or notoriously difficult to determine. Typically, people use the exponential prior in cryo-EM, which is also known as the smoothness prior, which basically tells you that if you don't have information, so in Fourier space, if you don't have information, instead of just letting noise take over, you just put those values to those Fourier coefficients to 0, which means that in real space you get these smooth reconstructions. So basically, I think all of you would agree that this cute duck on the right is a more desirable image than the one on the left. And the same goes for not maybe so cute molecular densities. And typically we use the FSC to determine the tau parameter here. And you can determine the FSC, for instance, using a hop-amp. Now, in the RELION 4 paper that we published last year, we present a few new ideas that are geared towards automated high-throughput single particle processing. And in this context, robustness is very important, but also speed, because you want to be able to keep up with your data acquisition. In the first CryoSpark paper, Ali Punjani et al. Presented a gradient-based optimization method they called SAGD, or stochastic average gradient descent. And although this method has multiple benefits compared to the expectation maximization approach, which is the other very commonly used algorithm, there has so far not been a very certain way presented to regularize reconstructions using this algorithm, other than perhaps heuristics. And we don't really know exactly how they do this in CryoSpark because the code is closed. But in the RELION 4 paper, we presented a null algorithm based on what is known as the variable metric approach, where we basically determine the shape of the update formula that I show here. And I'll promise this will be the only equation I'm going to be showing. And it's a pretty neat formula that incorporates the FSC. And if basically it says that if you trust in your FSC, you want to weight up the data fidelity term, and if you don't trust in it, you weight up the prior term. And right, and also we combined this with another layer of optimization inspired by the Adam algorithm, and these are some results showing an example for 2D classification. For 3D, we got good results as well, but for 2D, it was by far the biggest improvement. At the top, you have the old algorithm, the expectation maximization algorithm, and at the bottom, you have the VDAM algorithm, as we call it. And you get a lot more classes, so you can accommodate or you can account for a lot more heterogeneity in your data. And in addition to that, this is another example. In addition to that, we were able to get this about 6 times faster. So we kind of cover the robustness of the algorithm by having more classes, and we can better use our computational resources by having more classes as well, actually. And in addition, we also cover the speed part that is quite essential. Now, in addition to this algorithm in RELION 4, we made an effort to create fully automated reconstruction pipelines. 2D classification is a step in the pipeline that requires user input and is based on quite subjective criteria that people pick up through experience, basically. Basically, which 2D class should you select to go downstream into refinement. So to be able to kind of capture these subjective criteria, we opted for a data-driven approach to try to model this. So we processed over 18,000 2D class averages collected at the LME over the period of 4 years. We used then a convolutional neural network to supervise, to train it in a supervised manner to score the 2D classes between 0 and 1. And then we used a convolutional neural network to automatically select data subsets based on the 2D class averages. We are able to reconstruct 11 out of 12 test data sets fully automatically from Empire database. So although we're able to significantly improve the pipeline in terms of automation, and there are still quite a lot of issues. In particular, the 3D classification remains a major issue. It takes a lot of time and a lot of user input. People have to bring in different classes. You've probably seen these large graphics where people show how they combine different classes, different subsets to be able to get their final structure. These are also subjective things, and also the main reason for this is that 3D classification typically used is not robust enough. So you can't just trust the algorithm to give you the full analysis of your data. You have to kind of massage it to kind of work in the way you want it to. And this is not desirable, especially if we want to have high throughput pipelines where people more and more are collecting a lot more data and a lot of variations in their data. So we want to be able to address this. So we turn to some methods in modern machine learning that's seem to be showing quite a lot of promise. Ellen Zong implemented an approach where they use a variational autoencoder to better model conformational heterogeneity in the data. And the way this works is that you have an encoder and that you feed in the data to, and this extracts features and compresses this information into a very small vector called the latent space vector. And with additional information that you feed this together with additional information into a decoder, and the decoder takes it back into image space. And you then compare the output, the reconstructed image with your data, and then you backpropagate through this entire thing end to end, and you train this network. And this relates to representation learning, but primarily because you're learning the reconstruction as well as you're learning the representation of your data. So we want to be able to address the issues of 3D classification. Unfortunately, this approach is quite slow. So people have been using it for extended analysis of their data. It's very difficult. It's kind of impossible as it is today to incorporate this into a typical cryo-EM reconstruction pipeline and potentially replace 3D classification. And so after the RELION 4 paper, I started working on an alternative approach for doing something similar. And to be able to tell you about this, we need to make a distinction between explicit coordinate approach and the implicit coordinate approach. The cryo-dragon approach is what I call an explicit coordinate approach, where you, if you have your Fourier volume and you have your Fourier slice theorem, you know the projection of your image in this context. You know the projection of your image, and you put it into your 3D volume, your 3D Fourier space, and you get a slice. And then each of those pixels from your image end up somewhere in this 3D volume. And you take the pixel coordinates in this 3D volume, and you feed that into a feed-forward neural network or a multi-layer perceptron, together with the latent vector. And you ask for the network to give you a pixel value or a Fourier coefficient, a complex value, or it could also be a scalar value. And then you compare this to the pixel in your data. And you get an error that you then generate the gradients with, and you backpropagate through this thing and through the encoder as well. So basically, for each pixel in your image, if you have, like, for instance, a 200 times 200 image, for each image, you have to run this feed-forward neural network a lot of times for each image. So for instance, you have a 200 times 200 image, you would have to run the network around 30,000. You have to run the network about 30,000 times. And if you have a batch size of, say, 8 or 10, that's around 300,000 times you have to run this. You have to evaluate your network weights and then train it. So to avoid doing that, to avoid having to rerun this thing, we turn to this other approach that I call the implicit coordinate approach, where the network takes a latent vector and it generates a whole volume every time. So basically, for each time you run the network, it can generate the entire volume. And this might sound very inefficient because we're only, like, when we're training it, you have slices and you don't actually need to see the entire, you don't have to evaluate the entire volume. You only want to look at the slice that you have data for. So to be able to kind of solve that problem, we do something we call sparse backpropagation. And the way that works is simply you do a little analysis and you find those weights in your network that are affected by that specific subset of coordinates that you have data for. And you only backpropagate and you generate a gradient only for those specific network weights. And by doing this, we're able to train these networks with a smaller memory footprint. We can do larger batches, for instance. We can accumulate the gradients much easier. And also, we can do a bunch of other things in addition to efficiency. We can, for instance, query the network to generate a volume much quicker, much faster. With cryo-dragon, for instance, if you want to query, if you want to reconstruct an entire volume, you can't do it in one go. You have to reconstruct part of the volume, and then you store that partial volume, and then you run the network for another batch, and then build up the volume slowly. Whereas here you get the entire volume immediately. So what we can do now is that we can actually do a Fourier transform of the entire volume, go to real space, apply real space priors, like, for instance, solvent mask, and then we can differentiate through the Fourier transform and then into the network weights, and then differentiate, all the way to the encoder. And then that means that we can, for instance, have solvent mass. This is something people take for granted when they do 3D classification. And yeah, so we want to have the same features that we have in 3D classification as well. And yeah, and in addition to that, you can do a bunch of other things. You can do fast global angular searches. If we want to, replace 3D classification, we'll have to be able to do global searches because we don't know the angles beforehand. And with this, you would be able to do that almost as efficiently as we do it in 3D classification. Right. Also, the network capacity goes up. You can go to higher resolutions. This still needs to be evaluated, but theoretically, there is no limit. There's no network limit that limits resolution in the same way that CryoDragon does. So we basically, using this, we train the network and we compare it to CryoDragon, and we see that we get very similar results. This is for the Plasmodium ribosome data set, and yeah, in this data set, it's kind of an extended data set that has about almost 200,000 particles, and there's a bunch of garbage particles, and we wanted to see how it handles garbage. We see that CryoDragon and our method gets very similar results, although I think mine looks better because it's purple. But apart from the aesthetic part, we also were able to get this faster, about 3.5 times faster. Each epoch was about 4 minutes compared to about 15 minutes with CryoDragon. So we're kind of starting to hit the I/O limit, which means that we can now maybe do other computations instead, like for instance, global angular searches can be added to this. Right, yeah, so if then we look at, if we do like a little traversal through the latent space, we see that it captures the heterogeneity. In the data, we have the twist of the small subunit, and also the head swirl and a bunch of other things. And if we look at the garbage particles, you have like this gradient between particles that have basically nothing in them to particles that have only the large subunit. And then this is another ribosome example. I know it's only ribosomes, but sorry. So you'll have to settle with this, sorry. Yeah, so for this other data set that is only, this is the intermediates, the assembly intermediates data set of a ribosome. We see more heterogeneity, and we can see that it picks up, for instance, here you have different parts of the interfacial RNA being folded and unfolded for different parts of the latent space. So I would like to kind of round this up by mentioning that, so this is a simulated data set that we generated using a molecular dynamic trajectory. It's about 10 states that we extracted, and then we generated projection images and added noise and so on. And running this method on it, we see that after about 2 epochs with the training, so we have a training data set and validation data set. The training data set is what we train the network with, and the validation, we don't show it to the network, we just evaluate the network using to see what it gives. And after about 2 epochs, we see that the open and the closed states are separated into these 2 clusters over here. And that happens also in the validation data set. And after about 10 epochs, we see that the intermediate, or the in-between states between the open and closed states are separated into another cluster. This happens also for the validation data set. But after about 40 epochs, if we zoom in on those 2 figures, we see that the training data set have nicely separated. This is a PCA, I should say, of a high dimensional latent space. I think it was 10 dimensional. So these are much more separated actually if you do a different type of dimensionality reduction. But what's interesting is that even if you do a different type of dimensionality reduction, the validation data set starts kind of, the clustering starts falling apart. And this is simply because the encoder has stopped generalizing beyond the training data set, because it's sort of being overfitted, which is not desirable. You would preferably want to, have full statistical support for the clustering. So if you start clustering things up, you want to actually be able to say that I'm telling this apart from noise. this data set has a very high signal to noise ratio, so the effect is less severe, but for realistic data set, this should be even worse. So I'm just gonna mention this, and the point I'm trying to make is that in normal cryo-EM reconstruction, we have regularization we have to regularize the reconstructed density. But when we're using this kind of method, we also have to regularize. So in addition to the regularization of the reconstructed density, we're also reconstructing the representation of our data. So we need to think about regularization of the latent space as well. This is typically done using KL divergence in VAEs, but the weight of your KL divergence is typically just heuristically picked. And people historically they tweak it for each data set. And VAEs are typically not used per data set. So like you usually have like a really large data set, and then you train your VAE, and then you use that VAE to make an inference. Whereas here, for each data set, we're training a new VAE. And this means that we need to come up with better automated ways to determine how much we want to regularize our latent space, instead of assigning values and asking the user to kind of pick a value. Right, so basically to summarize this, in single particle analysis, we present this automated pipeline. We identify that there are issues, specifically in 3D classification, and then basically we're trying to address this by switching over to potentially another algorithmic candidate, another candidate of an algorithm that has higher expressive capacity and it can accommodate or account for larger heterogeneity, and by doing that, try to improve the robustness of the reconstruction algorithm. And this method has you can make faster volume queries, and it's actually quite fast. I didn't mention this, but you can actually like interactively click in latent space and get 3D volume reconstructed right next to it. I've showcased this to some people here, but I'm not going to give a live demo. Yeah, so basically, with this approach, we hope to kind of start approaching the stuff that we do in 3D classification, and potentially maybe replace it. But this poses new challenges in terms of, for instance, regularization that we need to think about. So I'm gonna round up by thanking people involved in this project. Shore's my advisor, and Kiarash, a PhD student, started in Shore's lab recently. And Johannes, we sit in the same room. These are machine learning people, so we have a lot of very bubbly discussions. And Jasenko, he's kind of left the field, but he kind of helped me a bit with the CUDA implementations I made for the kernels for the sparse backpropagation approach. And as well as Takanori, Lee, and Grigory that were involved in the RELION 4 paper. And I'd like to thank the organizers for letting me talk here today. Thank you.